So our essential question today is, what does it mean to find the limit of a function? How do I evaluate limits numerically, graphically, and analytically? So we've seen limits in pre-cal, and so let's remind ourselves of some notation first. The notation LIM, x approaches a of the function f of x is equal to L, says the limit of f of x as x approaches a equals L. And so what this means is that as our x values get closer and closer to the number a, the graph, or f of x, or y, gets closer and closer to the value L, okay? There are three ways that we learn to evaluate a limit in calculus. I'm not sure you learned all three of these ways in pre-cal, but we're going to talk about all three. The first is using numerical methods. So we call this numerically evaluating a limit. And what this basically means is we're going to use a table. The second way is to take a graphical approach. The third way is to use an analytical approach. And analytically, in our case, means we're going to use some form of algebra to manipulate the expression. A really important thing that you need to know when we do talk about limits is that whenever we work with limits algebraically, the first thing you should do always is direct substitute. Or evaluate the limit. And what that means is you should just plug in the value of x. Now, if you get an undefined or indeterminate answer, that tells me we need some sort of algebraic technique. And the last thing that I really want you to know before we dive in deeper is that you need to remember that a limit is a y value. Okay? So let's start by just talking about continuity and what a limit is in general. So we have three graphs here. And what I want you to know is that being a continuous function does not affect our limit. As long as our graph approaches that value from both sides, the limit exists. And so what this basically means is, let's say that I get in my car and I decide I want to drive to San Marcos. As long as I'm pointing my car at San Marcos, it doesn't matter whether I get there or not. Let's say that Coach Simino is on the other side of town and she decides she wants to drive to San Marcos too. It doesn't matter if she gets there, but what direction is she heading? She's heading to San Marcos. So both of us from either side are driving to San Marcos and pointing our cars in that direction, regardless of whether we actually get there or not. So let's look at three graphs. The first graph, here is our value of x, which we'll call a. And so as we get closer to a, and from our x values on the left side, you can see I'm going to get really close to a y value of L. And from the right-hand side of A, as I travel down my graph, I can see that I again get close to a y value of A. So my limit as x approaches A from both sides of the function f of x is equal to the y value of L. Okay? Now in our next graph, it's kind of hard to see, so I'm going to zoom in for a second. You can see that I've got a removable discontinuity here. So there is a hole in this graph. And also there is a point that is down here that has been removed from the function. Okay? So again, let's say I'm traveling on my graph. I'm pointing my car towards the x value of A. Even though there's not a point there, I'm getting closer and closer to a y value of L. And from the right-hand side, I'm again getting closer and closer to an x value of A, and I'm getting closer and closer to a y value of L. So again, my limit as x approaches a of my function f of x is equal to L, even though there is no point at that point. And even though this point down here is at a different value, as long as I'm pointing my function in the direction and getting close to that y value of L, that doesn't matter. The limit is L. So in my third example, I don't have a point that's been added, but again, I have this removable discontinuity or hole in my graph. And so again, I'm going to get closer to A from the left-hand side of it, and I can see I'm getting close to this y value of L, even though it's not there. And from the right-hand side, I get closer and closer to A. So my limit, as I get close to A of my function, has a y value of L. Okay, so on this note of continuity, which we'll continue to talk more about being a continuous function later, you've heard me say from the right side and from the left side. So let's talk about sided limits. So we can actually evaluate one-sided limits. And when we do talk about one-sided limits, the left and the right sided limit must match. If they do, the limit exists. If the two sides do not merge towards the same value, then the overall limit does not exist at that x value. It is acceptable to use the words no limit exists. You can also use NLE, and I'm going to also write in here DNE. DNE is also a acceptable notation. So the way that I would explain this is, let's say that, Coach Simino gets in her car and she drives towards San Antonio, but I get in my car and I drive towards San Marcos. Now, one side is going to San Marcos and the other side is going to San Antonio. And because we're not headed in the same direction, our limit overall does not exist. So we're going to introduce some notation. Let's start with that notation. L sub L is a notation used for the limit on the left-hand side. And we're going to put an A and a little negative sign right here. And I want you to know that the negative sign comes after the function or after the value. So don't put the negative in front because then it'll look like a negative number. We're going to put the negative after the number. And so this is the notation we're going to use for a left-hand limit. A right-sided limit is going to be L sub R. And we're going to say the limit as x approaches A, and then we're going to put a positive next to it of the function f of x. Now, really important that you know that we want to include this thing right here. We would never have a square root with nothing in it. We would never have a limit as x approaches something and not say what we're taking the limit of. So it's really important that you know you have to fill that in. Now, an overall limit exists if the limit from the left equals the limit from the right. An overall limit does not exist if the limit from the left does not equal the limit from the right. And so what does that look like? Let's make a real pretty graph here. Let's actually do something with like a jump discontinuity. And let's say that this point right here is our value A, okay? So let's approach it from either side. As I get closer to A from the left-hand side, I'm approaching whatever this y value is right here. As I approach A from the right-hand side, I'm approaching this y value. And so in this case, the limit from the left does not equal the limit from the right. And I can have those sided limits, but the overall limit does not exist, okay? So let's start with our venture into how to find limits. So before we do any kind of graphical limits, let's actually talk about method number 1, which was a numerical approach. So we're going to evaluate limits numerically. So you're going to want to get your calculator handy, okay? So what we're going to do here is we're going to make a table of values, okay? So really, really important that you might want to know, we're going to go and set up our calculator and I'm going to try and explain this as I do it. So when you're looking at your calculator, I can't project my calculator on this screen, so you're going to have to listen very carefully. If you go to second and the window button, you're going to change your independent variable to ask, okay? You're going to change your independent variable to ask, okay? So you heard me say earlier that the first thing that we should attempt to do is we should always try and plug in. So I want you to see what happens if I plug in here. If I plug into this function, I get -3 plus 4, which is +1. Square root of 1 is 1, 1 minus 1 is 0. And then in the bottom, I also get 0. Well, guys, you can't divide by 0. We call this an indeterminate form. Now, that doesn't mean that this thing doesn't have a limit, because guess what? It does have a limit. So what I'm going to ask you to do is I want you to take this thing right here, making sure to use parentheses, okay? And I want you to take that expression right here, and I want you to go load that into your y1, okay? And so I'm actually going to pull up Desmos to be able to do this with you. And I'm going to type in square root x plus 4. Let's get out of the square root, minus 1. And then we're going to divide. Oop, I need parentheses. So let me go up here and throw some parentheses. And we're going to divide this whole thing by parentheses x plus 3. Okay, and graph it. Now, you can't tell it here, but there is actually a hole at -3. So there is no value in my function at -3, okay? So what I want to do is in my notes, I've asked you to fill in a table. And so we're going to use a tabular approach to figure out what the limit of this thing is. So in Desmos, to do that, I'm going to go to the little cog in the right-hand corner right here, and I'm going to push this little table. And the nice thing about Desmos is I can now type in my values. So I'm going to type in -3.1. And then I'm going to go to the next one, and I'm going to type in -3.01. And then I'm going to go to the next one and get -3.001. And then I'm going to say -2.999 and -2.99. And finally, -2.9. And what I don't think you realize you're doing is you're getting closer and closer to -3 from both sides of the graph. And I hope that you can see here on my screen that I'm getting really, really close to a value, even though if I go to my table and I type in -2, it says, not -2, -3, it says undefined. There's no value there. But I can guess what this limit is based on these values. So going back to my notes and filling these in, I've got 0.513, 0.501, 0.500, 0.499, 0.499, and 0.488. And just to kind of sketch the graph over here, at -3, there was a hole in the graph. And I could actually tell, even though -3 is right here, I can see that as I get closer and closer to -3 from both sides, the y value appears to be 1/2. So what that tells me is my limit from the left and my limit from the right are the same, and my limit is 1/2. That's my answer, okay? So what I'm going to ask you to do now, and on your, you could do the same thing on your table in your graphing calculators, or you can use Desmos just like I did. I'm going to ask you to do this one now independently, pressing pause on the video and trying this one independently, okay? All right, so if you've pressed play, I am going to hope that you have found an answer, and we will talk about that in class. So you should have this table filled in. You should have an overall limit as your answer and a little sketch of your graph filled in on your notes, and we'll talk about that in class. So I want to show you some more examples of a graphical approach. And so here we're looking at a piecewise function. And in this piecewise function, I can see that I have a point at 2, 3. And then I have this quadratic function right here where x cannot be 2. And so when you are in Algebra 2 and your Algebra 2 teacher said you really need to know all of your transformations by heart, this is kind of where she was talking about, or he, knowing how to graph these functions without a calculator, because you will not have a calculator for these kinds of things. And so let's make a quick sketch. I would hope everyone could tell me that's the parent function that has been moved up 1 unit. So that means at 0, 1, and 1, 2, and negative 1, 2. And then instead of 2, 4, we're now at 2, 5, and negative 2, 5. And so here is my really rough draft of a quadratic function. And it has now a discontinuity at 2. So that means that this point right here is actually going to be an open circle. And instead of having the point at 2, 5, we're going to now put a point at 2, 3 right here. Okay? And so I can actually use this graph to answer the question because I want to know what is the limit as I approach 2. So from the left side of my graph, I'm going to get close to 2. And from the right side of my graph, I'm going to get close to 2. And I can see that in both cases, I'm getting close to that hole. And that hole is a y value of 5. And 5 is my answer. It does not matter that there's a point here, guys. That is my answer. Okay? So a discontinuous graph does not affect the limit. So I've got one more for us to do, and this one's kind of tricky. And if you have a highlighter or something in color, I would put a big giant star by this. This graph of this function, I guarantee you, is going to happen and show up on the AP exam. So you need to know this graph. So we've never looked at something like this before. And what I want you to know is whenever you see an absolute value function, an absolute value function is a piecewise graph. So we're going to actually turn this into a piecewise graph. So remember that absolute values can be positive and they can be negative. So positive x plus 3 over x plus 3. And this graph is going to be valid anytime we are bigger than negative 3. Okay, because negative 3 would be what makes this 0 over 0. And I also know that absolute values can now be negative, right? So we have a negative x plus 3 over x plus 3. And this is going to be anytime that x is less than negative 3. So how do I know that this is what it does? You're going to make a positive version and you're going to make a negative version when you see an absolute value. And you're going to split it at the value that makes this highlighted piece 0, okay? Now, I want you to think about this. First off, this is not going to look like an absolute value graph. It's not going to be a V-shaped function. I want you to think about how I could simplify this piecewise, okay? So if I could simplify this, when you have x plus 3 over x plus 3, that's just 1. So I'm going to graph 1 whenever x is bigger than negative 3. And I can take this bottom piece, and guys, that's just going to simplify to negative 1 anytime x is less than negative 3. So graphically, what we've just done here is here's negative 3. I'm going to be at positive 1, and I'm going to be at negative 1. And this graph is so important. This graph right here will occur on the AP exam. So guys, this is just two constant functions. This one's at 1 and this one's at negative 1, and they both have open holes here. So now I can answer this question. It wants me to find the limit as x approaches negative 3 of this function, x plus 3 over x plus 3. And let's evaluate it from both sides. As I get close to negative 3 from the left, I can see that my limit from the left appears to be, as x approaches negative 3 from the left of f of x, looks like